Hello everyone. In this video we're going to be solving a Diophantine equation. We have 4 to the power x minus 25 to the power y equals 39. X and y are integers. And we're going to solve this Diophantine equation. Diophantine equations have usually integer solutions, and sometimes there are no solutions, sometimes there are finitely many, sometimes there are infinitely many solutions. Let's go ahead and explore this equation further. So first thing that I'd like to do is notice that 4 and 25 are both perfect squares. So we can go ahead and write them as 2 to the second power and 5 to the second power. And of course we have other exponents, and this is equal to 39. So I'm going to go ahead and solve this equation, find all the solutions, or if there are no solutions, I'm just going to indicate that. And I'll also show you a graph of this relation, which is kind of interesting. All right, so notice that we have powers of powers. So think about the property of powers. When we have a to the power b to the power c, it means a to the power bc, but it can also be written as a to the power c to the power b. In other words, the powers can be switched. Here I'm going to do that. So let's write the 2 to the power x as 2 to the power x to the power 2 minus, and this second one as 5 to the power y to the power 2 equals 39. Now the good thing about that is I can't really do anything to a difference of, something to the power x minus something to the power y, but if they're both squares, I can definitely do something. And what is that called? Difference of two squares. Remember, I told you it's an important identity and we use that a lot, so make sure you have it memorized. Okay, so let's go ahead and do that now. We have a as our 2 to the power x and b as the second term, so we can write this as 2 to the power x plus 5 to the power y multiplied by 2 to the power x minus 5 to the power y, and the result is 39. Obviously you could take the original equation and guess, but that would not guarantee all the solutions. How would you be sure, right? So that's why we need to kind of go through this process and check that we're finding or looking through all the solutions. Okay. Now one fact that you have to consider here is that this factor is greater than the other factor. Why? 2 to the power x plus 5 to the power y is greater than 2 to the x minus 5 to the y. Because if you think about it, when these two cancel out, 2 times 5 to the y is greater than 0. That's a true statement. And this is reversible, right? Makes sense? Okay, so obviously the sum is going to be greater than that. So what do we do with that? We're going to go ahead and factor 39. 39 can be factored in a few number of ways. But we have to make sure that the first factor is always larger. 39 is a perfect square, so they're not going to be equal. That would indicate 5 to the y is 0, but that's not going to happen. But anyways, this can be 39 times 1 or 13 times 3. Since 39 is a product of two primes, those are the only two ways we can factor it, right? Because the first factor, remember, and by the way, this is what I mean by the first factor, is going to be greater. All right, so let's go ahead and set up a system using this. So this means the first factor equals 39 and the second factor equals 1. Let's go ahead and try to solve this as a system. To solve the system, it's very easy. You can just eliminate 5 to the y, and this gives you 2 times 2 to the power x equals 40 and 2 to the power x equals 20. We can find the x value using logs or ln or whatever, but it's not going to be an integer because 2 to the power x is obviously 20 is greater than 16, which is 2 to the 4th, and less than 32, which is 2 to the 5th. So x is between 4 and 5. It's a number 4 point something, and it's irrational. It's also transcendental, I believe, right, because of the logs. Anyways, it's not an integer. Nobody cares, right? That's what we care about. That's what matters. So this didn't give us any integer solutions. No integers will satisfy this. Okay. Let's take a look at the second case. Second case told us, hey, the first factor can be 13 and the second factor can be 3, this one, right? So we can go ahead and solve this. 5 to the y cancels out again, just exact same thing happens. But 13 plus 3 is 16, which is nice because 16 is a power of 2. And when you divide by 2, 8 is also a power of 2, right? So we get a integer solution. Yay! If we didn't get a solution from here, then this equation would have no integer solutions. X equals 3. Now, how do you find the y value? You can plug it in. Substitute x equals 3, you get 8, subtract from 13, 5. 5 to the y is 1, and y is equal to, 5 to the y is 5, y is equal to 1. I'm ahead of myself. So that's going to be the only solution pair that you're getting. All right, let's go ahead and take a look at the graph of this relation, which is 4 to the x minus 25 to the y equals 39. Now, I know some of you are kind of asking the question, what if this isn't like 375? Okay, in that case, you can still look for solutions. You can look for upper and lower bounds. You can also use modular arithmetic. I don't know if I shared with you, but I also made a video on modular arithmetic. Maybe I'll share with you if I didn't. Anyways, but yeah, there are ways to solve it, but some equations are harder, obviously, than others. So here's the graph of the relation 4 to the x minus 25 to the y equals 39. And why did I mark the only single point 3, 1? Because that's the only point with integer coordinates, and those are called lattice points. Lattice points are points with integer coordinates, and we have a single solution for this equation. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you tomorrow with another video. Until then, be safe, take care, and bye-bye.